Welcome to the tutorial on semantic parsing with combinatory categorial grammar. My name is Yoav Artzi, and this tutorial was originally presented in the annual meeting of the Association for Computational Linguistics in Sofia, Bulgaria in 2013. It was originally presented by myself, Nicholas Fitzgerald, and Luke Zellermoyer. And this video version of the tutorial is divided into short videos according to topics. The complete series of videos and the slides in PDF format are available on the tutorial website. So today, it's all going to be about semantic parsing. But first of all, I would like to place us in context in relation to other tasks in NLP. Specifically, I would like to look at the notion of meaning that semantic parsing adopts. So we can look at this spectrum where we are trying to recover more and more informative meaning representations from text. So on the one end of the spectrum, we'll have tasks such as information extraction, where we are trying to recover specific bits of information from text, such as unary or binary relations. If we continue along this spectrum, we encounter a large set of broad-covered semantic tasks, such as summarization. And if we continue even further, we reach semantic parsing, where our goal is to recover the complete meaning representation of a sentence. And what do I mean when I say the complete meaning representation is something that I will answer in a minute. But first of all, I would like to look at example tasks. So for example, we can take natural language query to a database, interpret it, execute it against database, and return the entries that are the answer to this query. Or we can instruct a robot navigating an environment where we give the robot natural language instructions, and we will expect the robot to process the instructions, interpret them in a way that allows it to do the necessary planning to complete the task. So what do I mean when I say that we want to recover the complete meaning representation? So of course, what is the complete meaning of a sentence is a contentious philosophical issue. But today we are going to sideline a lot of this discussion, and we're going to define it in a very task-specific way. So the complete meaning of a sentence is the meaning that is sufficient to complete a task. So for example, in the case of database queries, it's the meaning that is sufficient to construct the SQL or Sparkle query required to execute against database, so we can return the correct response. When we're instructing a robot, this will be the complete meaning will be the meaning that is sufficient for the robot to do the necessary planning to achieve its goal. Now, a common thread for all semantic parsing tasks is the logical form representation. And this logical form representation is not simply paired with the sentences. It is gradually constructed by combining the meaning of words and phrases in the sentence. So for example, if we look at the logical form here representing the meaning of the sentence, we can see that the word chair contributes this part of the logical form. The word forward contributes this part. The expression 3 steps contributes this part. And finally, the expression the sofa contributes this part. Now, of course, there are other parts of the logical form that come from other parts of the sentence. But what's important, what I'd like you to take away from this example, is the compositional nature of the process. The meanings of specific words and phrases are gradually composed to create the meaning of the complete sentence. So, given that our goal is to take sentences and recover the logical form representation, we can define a learning task where, given sentences and some sort of supervision, we would like to learn a function from sentences to logical form representing their meaning. And in the simplest case, what we refer to as supervised learning, we'll have access to the logical form representing the meaning of the sentence. However, we'll also show more complex cases that use weaker supervision. For example, instructions paired with demonstrations of people executing them. Semantic parsing is a challenging task, and we are going to break it along to 3 major problems: parsing, learning, and modeling. Along each of these dimensions, the number of approaches were proposed in the past, and first I would like to give you a quick overview of the versatility of approaches that exist in the literature. So as far as the parsing problem, what we need to do is first choose the grammar formalism we would like to use and the inference procedure that we are going to use. And there are a number of approaches that propose, starting from inductive logic programming that was first proposed by Zell and Mooney in 1996. And then later on we see approaches such as synchronous context-free grammars being used, combinatorial categorial grammars with CKY chart parsing, constrained optimization with integer linear programming, and dependency-based compositional semantics with projective dependency parsing. When we look at the learning problem, we need first to decide what kind of supervision we would like to assume access to. And the first learning approach that we are familiar with was proposed by Miller et al. As early as 1994 and used annotated parse trees. However, more recent approaches use latent variable methods and assume access to training data that includes pairs of sentences and logical forms, or more weaker forms of supervision, such as question-answer pairs, instruction-demonstration pairs, access to conversation logs that contain system recovery attempts, and access to visual sensors. And finally, as far as the semantic modeling, we need to decide what logical language we are going to use and how we are going to use it to model the meaning of language. And again, there are a number of approaches that were proposed on how to do this, using a variable-free logic or high-order logic, and more recently, relational algebra and graphical models. Today, we are going to focus on one general approach that makes specific decisions along each of these dimensions. For parsing, we will use combinatorial categorial grammar and a parsing algorithm that is very similar to CKY chart parsing. We will show you how a unified learning algorithm and apply it to both supervised and weakly supervised learning scenarios. And finally, for modeling semantics, we will use lambda calculus, and we'll discuss a number of best practices on how to model the meaning of language. So the tutorial is going to be divided along these three dimensions. In the first part, we look at parsing, then at the learning problem, and finally at how to model semantics. In the first part, we'll start with a very short introduction to lambda calculus, and then we'll introduce combinatorial categorial grammars, define a linear model over these kind of grammars, and finally introduce the concept of factored lexicon, which is a more compact way to represent these kind of grammars. In the second part, we will look at the learning problem, and we will start with a quick refresh of structured perceptron, and then introduce a unified learning algorithm, and we will apply it to two scenarios, to the supervised scenario, where we have access to sentences paired with logical forms, and to the more varied weakly supervised learning scenario. And finally, in the third and last part of the tutorial, we'll look at the semantic modeling problem. And we will do this by looking at a few domains, databases, physical objects, referring to physical objects in environment, and executing natural language instructions. And what we're going to do is, by going through this database, through these domains, we will introduce various best practices on how to model the meaning of language. This tutorial is accompanied by the University of Washington Semantic Parsing Framework. It's an open source semantic parsing framework. It's available online. It's implemented in Java, and it includes a semantic parsing algorithm, a flexible high-order logical representation language, and a number of learning algorithms to learn from both supervised and weakly supervised data. It includes ready-to-run experiments, so we hope that you will download the code, run the experiments, and see how learning is done for this kind of problem and what the output model actually looks like. In the first part of the tutorial, we're going to look at the parsing problem. We will start by reviewing lambda calculus and its typed variant, and then provide you a short introduction to combinatory categorial grammar, or CCGs. We'll finally describe how a factor representation of CCG lexicons allows us to represent this kind of grammar in a more compact and general way. So we will start with lambda calculus. Lambda calculus is a variant of high-order logic, and that means arguments can be functions and not only simple entities. It uses the lambda abstraction to denote anonymous function calls, to denote anonymous function abstraction, and it was originally proposed by Alonzo Church in 1932. Lambda calculus has 4 base cases: logical constant, variable, literal, and lambda term. And I'm going to define each of them in turn. So we will start with the logical constants. Logical constants can represent objects in the world, and these objects can be simple, such as cities, states, mountains, or directions, and they can be complex, where they represent relations between different objects. For example, located in, departure date, and so on. In addition to constants, we will have variables. And variables are similar to constants in that they point to objects in the world. However, unlike constants, the exact value of a variable is not predetermined. And we will denote variable using lowercase letters. The third case of lambda calculus is the literal, and literals represent the application of a function to a list of arguments. And therefore, a literal has 2 parts. It has the predicate, which denotes the function that is being applied, and it's a logical expression. And it has a list of arguments, which is basically a list of logical expressions. The final case of lambda calculus are lambda terms. And lambda terms are like anonymous function calls in functional programming language. They basically bind a variable and define its scope. And to allow multiple variables, we simply repeat and apply lambda terms one on top of the other. So a lambda term has 3 parts. It has the lambda operator, the variable that it binds, and the body. And for all these to mean something, the body must include references to the variables declared in the operator. So lambda calculus is different from first-order logic in what we saw, that we are missing the base case of quantifiers. In lambda calculus, quantifiers are not defined as a primitive type. They are natural members of the logic. They are simply constants that they are simply represented as constants. And this means that lambda calculus subsumes first-order logic, and everything that we can express in first-order logic, we can express in lambda calculus. Now, just a comment about how we write these expressions. We're going to use a bit of syntactic sugaring in the rest of the tutorial today. And so I'm just putting this slide for reference. We'll have syntactic sugaring for disjunctions and conjunctions and negations. And finally, we will write quantifiers similar to the way they are written in first-order logic. Before we continue, I would like us to look at these 3 logical forms and ask ourselves, do they make sense? Would we like to consider these lambda calculus expressions when we are considering the space of possible interpretations for a sentence? And we intentionally don't provide here this exact meaning of constants, but we name the constants in a way that is fairly indicative of what they're trying to say. So if we look at the first logical form, we can see that it's probably something of type flight, because we have the predicate flight here, and so we can say that maybe the predicate 2 is this destination of the flight. However, the destination of the flight seems to go to some constant that seems to indicate some kind of movement. So this logical form doesn't really make any sense, because you can't really have flights that go to actions. So we would like to not consider this logical form. On the other hand, if we look at the second case, things actually make much more sense. Again, we have a flight here, but this time this flight is going to New York City, which makes absolute sense when we're talking about flight. So this logical form looks great to us. We probably would like to consider that. And finally, if we look at the third logical form, things really don't make any sense. So we are going to use the constant in New York City to basically, as a predicate, basically giving us the sort of like the type of the variable x, and then you're going to use this x again here as a predicate, and it's going to take two relations, to and move. Yes, so the third logical form also doesn't make sense. So what we would like is we would like to try to avoid this kind of logical forms that don't make sense, like the first and third case. And this is really going to constrain the space of potential interpretations for a sentence. So what we're going to do is we're going to use simply typed lambda calculus. And it's a very similar mechanism to lambda calculus. The only difference is it's typed. And it was originally proposed, again by Alonzo Church in 1940, to avoid some of the paradoxes in lambda calculus. And from now on, we're going to conflate the two terms. So from now on, when I say lambda calculus, I'm actually going to mean simply typed lambda calculus. So our typing system includes primitive types such as truth value and entity, and truth value or entity, and also complex types. The complex types that are representing functions, and they are composed by taking types and using the typing operator, the comma. And the typing operator is going to define one type as the domain of the function, and the other is the range. So if we look at the first example, we can see that what we can see here, that this basically means a function from E to T. So it's a function that takes entities and returns true or false. The second case is more complex. Here we have a function that takes functions from E to T and returns an entity. We also for this typing hierarchy, we'll have a single inheritance relation that is going to define a typing hierarchy, and this typing hierarchy can go arbitrarily deep, and can really provide details and can provide details about types and inheritance between them. And later on, we will see how this kind of typing hierarchy is going to help us to use weak supervision for learning for learning grammars for semantic parsing. Now, another final note about notation: we are not going to specify the typing information. It's usually obvious from a context. So the logical forms from now on, in most cases, are going to look like the one that we see here, with no typing information. So we defined this relatively powerful logical representation language, and the question is what we can represent with this kind of logic. So for example, we can represent queries for a database system. We can represent user requests in a dialogue system. And more recently, we showed that we can represent instructional language, for example, when instructing a robot navigating in some kind of map. So we have this fairly flexible representation, and it's fairly powerful, and it's expressive enough to capture the complexity of natural language. The big question, of course, is how the constants that we are using should look like. And this is what we call the modeling question, and we are going to look at this at the last part of the tutorial today. So now we know how to read these logical forms. The next thing I would like to show you is how we can construct these logical forms from language. And the process I'm going to define is going to follow the structure of language, gradually combining the meaning of words to construct these logical forms that represent the meaning of sentences. The grammar formalism that we will use is called Combinatory Categorial Grammar, or CCG. It was first introduced by Mark Steedman, and the reference section includes a number of references that you can follow if you're interested in further reading about it. This is a very simple CCG parse tree, and I'd like to quickly go through it just to give you a quick idea of the overall structure of the grammar and the parsing process. Later on, I'll explain this process in detail. So this parse tree is read from top to bottom. And the first thing that is happening is that we pair words or phrases in the sentence with categories representing their meaning. And this complex structure capture the meaning of words, and they include both the syntactic component and the semantic component. Later on, in the process that we see going down here, these categories are gradually combined to create a logical form that captures the complete meaning of a sentence. And this is the logical form that we see here at the bottom. So CCG is a categorial formalism. And this means that most of the information is in the parse tree nodes rather than in the rules combining these nodes. So these nodes are combined using a small set of rules. And this is in contrast to context-free grammar, where we have a few symbols, but many rules to combine them. CCG provides a transparent interface between syntax and semantics, and it is designed with computation in mind. It's a member of a larger equivalence group of mildly context-sensitive grammar, such as tree-adjoining grammar, head grammars, and linear index grammars. And in the Chomsky hierarchy, it's between context-free to context-dependent grammar, and some linguists believe this is the right balance to capture human language. The basic building block of CCG is the CCG category. And the CCG category includes two components, the syntax and semantics. The syntactic component expresses the syntactic role the category represents. And it can be a small number of primitive symbols, such as noun, adjectives, or prepositional phrases, or it can be any of these symbols combined using two operators, the backward and forward slash, to create more complex syntactic categories. And the slash basically specify the argument order and directionality. The second component of the category is the semantics, and this is the logical form, and it varies and depends on the logical language you choose to use. In our case, it's a lambda calculus expression. And it's important to note that there is an alignment between the syntactic type and the semantic type. And this is going to allow us to jointly operate both on the syntax and the semantics when constructing CCG parse trees. To pair meaning with words, we use lexical entries. And a lexical entry has two components, the natural language, which is a word or a phrase, and the CCG category that captures its meaning. And the CCG category captures both the syntactic role of the word and its semantic meaning. These lexical entries are part of a larger set of lexical entries in a grammar, and this is called a lexicon. And lexical entries are used very similarly to part-of-speech tags in context-free grammars. They are the nodes of the parse tree. It's the first step during parsing. So before we start looking at trees, I would like to correlate CCGs to the more familiar context-free grammars. So in CFGs, we have many rules, and these rules carry most of the information. In contrast, in CCGs, we have very few rules. CCG is a categorical formalism, and most of the information is in the nodes in the parse trees. In parse tree nodes in CFGs are non-terminals. It's a closed set of symbols. In contrast, in CCGs, these are complex categories that carry both syntactic and semantic information. The space of syntactic symbols in CFGs, we have a few dozen symbols, often part of speech tags. And in CCGs, we have a handful of primitive symbols, but we can combine them using the backward and forward slash to create arbitrarily complex syntactic categories. And finally, the parsing process in CFGs starts by pairing words to part of speech tags. And the equivalent in CCGs is using the lexicon to pair words and phrases to categories. So let's look at a very simple example first. And as we said, the first step of parsing is to pair categories to words and phrases from the sentence. So we use the lexicon to pair words in this short sentence to candidate categories. For example, for fun, we will have this adjective category. Next, we will need to combine these categories. And for that, we use a small set of operations. These operations take one or two CCG categories, so they are unary or binary, and output a single CCG category. They operate jointly on the syntactic and the semantic components of the categories, and they often, as we will see, mirror natural logic operations. So, for example, the first operation we're going to look at is application. An application is equivalent to functional application in logic. It has an argument, and this is this category here on the left in the topmost row. It has a function category, and then this is the result. So as we can see, the function category expects a B category on the left, and this is indicated by the directionality of the slash. It's a backward slash. And once it consumes the argument, it's going to return the syntactic type A, as we can see on the other side of the slash. And indeed, we see that the result category includes the syntactic category A. And as far as the semantics, what we see is a very simple logical application. So F is applied to G. And this rule basically has two versions according to the directionality. It can be a backward application or forward application. And this is controlled by, and this is indicated by this the directionality of the triangular parenthesis on the right. This is determined by the directionality of the slash in the function category. Okay, so back to our example. So we matched categories to words using the lexicon, and next we need to start combining them. So we can start by using application. Specifically, we will use forward application to combine the category of is with the category of fun. And we're going to get the output category that is marked here below them. So as we can see, the syntactic form in the category of is expects an adjective on the right. And this directionality is coming from the fact that we have a forward slash there. And once it consumes this adjective, it's going to return the component of the syntax that is on the other side of the slash. And indeed, this is the result that we see here. This is the syntactic form that we see at the result category. As far as the logical form, what we see here is simple functional application. So the category of the semantic form of is consuming as argument the semantic form of fun, giving us this result. And now we can apply application again, this time backward application, where the functional category this time is the result from the previous application, and the argument is the category of the word CCG, and we conclude our parsing process. We get a category that has a syntactic form of sentence and a logical form that captures the meaning of the complete sentence. We showed a simple example of how to parse with CCG. And in this example, including forward and backward application, and using lexical entries to assign categories to words and phrases in the sentence. And we can do quite a lot using only these simple rules. But CCG is actually much more powerful, and it supports handling phenomena that are relatively difficult to handle with context-free grammar, such as non-standard coordination. To handle these kind of complexities, we add a few more general operations. So let's start by looking at this example at this phrase here, square blue or round yellow pillow, and try to think how you would like to combine the words and phrases in this sentence to get the meaning of the complete phrase. So the first thing we want to do is we want to combine the pairs of adjectives. So we would like to combine round yellow together, and we would like to combine square blue together, and then we would like to use this coordination and we'll have this entire structure coordinated where the two pairs of adjectives that were combined are now coordinated. And finally, this coordinated structure is supposed to modify the noun pillow. So in addition to application, we're going to add two more rules that are going to give us the ability to do functional composition. And just like in the case of application, we'll have two directions: forward composition and backward composition. And this composition rules are equivalent to functional composition. So if we compose the function f, with the function g, the composed structure is going to be f composed to g. And if you can see, as far as the syntax, we can see that f expects a b on the right, where g, once it consumes c on the right, returns b. So b disappears when the two categories are composed. It's now implicit in the composed structure, and we get a expecting c. And as far as the semantic, we have simple functional composition, which will give us this structure here. And the slides include, at the end, a supplementary slide that shows formally how to do functional composition in lambda calculus. So in addition to composition and application, we also support a number of unary operations. And these unary operations are going to shift or change the type of a category. Basically, what these kind of operations do is allow us to maintain a more compact lexicon. Instead of accounting and for every possible way a word can be used in a sentence, we're going to account for some of these cases using this kind of rules. So the lexicon is not required to provide all forms. And later on, when we will show how to learn the lexicon, this basically means that we can learn better from limited data, as we don't have to see every word appearing in every role every time. So the lexicon can only contain the more basic forms of words. So for example, we'll have a rule for adjectives, and these rules, they consume a single category and return a single category. So if you consume an adjective, we would return a category that modifies a noun and expects a noun on its right, since in English, adjectives appear before nouns. We'll also have a rule for a prepositional phrase that expects changes the type to expect a noun on the left, an adverbial phrase that changes the adverbial phrase to expect a sentence on the left. And we can also handle more complex phenomena, such as topicalization, where an adverbial phrase is shifted to expect a sentence on the right. In addition, we also have special entries and rules for coordination. So we're going to mark coordinating lexical entries on the lexicon, and we'll have specific rules that use this kind of categories to perform coordinations, and we're going to mark that specifically on the parser, as we will soon see. So let's go back and walk through the complex phrase that motivated this addition of rules to the grammar. So the phrase, to remind you, is square blue or round yellow pillow. And the first thing we are going to do is we are going to use lexical entries from the lexicon to get the initial categories for the words in the sentence. So for example, for the word square, we are going to assign this adjectival category, and for the word pillow, we assign this noun category. And now we are going to start applying the rules that we just defined. So the first thing we are going to do is we are going to apply a type shifting operation to the adjective square. So we are going to shift the category of the adjective square to a more complex category that expects a noun on the right. And similarly, we are going to apply the same rule to all the adjectives in the adjectives in the phrase. And we are immediately going to see how it will allow us to start combining these adjectives before they actually combine with a noun. Okay, so now that we have all the adjectives in a higher form that expects an argument, we can use forward composition to compose the pairs of adjectives. So for example, the adjective round is composed with the adjective yellow, and together their composition, using forward composition, gives us this complex category that packs the two adjectives and expects a noun on the right. And similarly, we see square and blue compose to give us again this more complex category that expects a noun on the right. Now we apply our handling of coordination. So we take the two composed pairs and combine them into a single category that captures the coordination between the two composed pairs of adjectives. And finally, we apply forward application so to allow this complex structure to modify the noun. And we get a logical form here at the bottom that captures the meaning of the complete phrase. Now in general, parsing with this kind of grammars is a highly ambiguous process. Given a sentence X, we are going to have many potential parse trees, including many potential parse trees Y, each one including a logical form Z. This kind of ambiguity can come from the lexicon, where usually each word has a number of meanings assigned to it, number of categories. Or it can come from how we decide to apply the parsing operations, the rules that we define, so which lead to many potential parsing decisions. And this leads to many potential parse trees and logical forms. To select a single parse tree, we define a linear model. Our linear model includes a lexicon, a feature vector, a feature function that takes a sentence and a parse tree and computes a feature vector and a weight vector. And given a sentence X and a lexicon, we select the best parse Y by maximizing the product of the feature vector and the weight vector. Now in general, as far as parsing algorithms, for syntax only, CCG has polynomial time CKY style algorithms. However, parsing with the semantics requires us to maintain the entire category as the chart signature when doing CKY style parsing. And this is going to lead to an explosion in the chart. So in practice, what we do is we use beam search and prune each span to maintain only the top n categories. Now this is going to be approximate, but it will provide us polynomial time parsing, and in practice it leads to fairly good results. So this was a short review of CCG, and there is a lot more on this formalism that you can know. And Mark Steedman from the University of Edinburgh published a number of books on the topic, and in these cover more operations such as type raising, cross composition, and generalized composition that handle more complex phenomena in English and phenomena that are more common in other languages. And recently, CCG was applied to handling other compositional domains, such as compositional handling of intonation, and even recovering the structure of jazz music. As we just saw, in combinatorial categorial grammars, the lexicon is a key component. In this lexicon, natural language words and phrases are paired with CCG categories. And it's often the case that we see multiple categories paired with a word or a phrase. And this presents a difficult learning challenge where we have to observe every word and phrase paired with every category that is possible for it during learning. And this is difficult with limited amount of training data. However, luckily, these kind of lexicons contain quite a bit of structural repetitions. And what we're going to show you now is how we can take advantage of these repetitions to overcome this difficulty of learning with limited data. And we'll do this by presenting a factored representation of CCG lexicons. So let's start by looking at a few examples. Here we have three phrases: the house dog, the dog of the house, and the garden dog. The first two phrases their meaning is represented using this logical form here that we see. And the meaning for the third phrase is represented by the second logical form. Now, if we look at the lexical entries that are used to construct these logical forms, for the first phrase, for the word house, we can use a lexical entry that pairs the word house and treats it as an adjective, with the category with this logical form. In contrast, in the second phrase, the dog of the house, the word house is treated as a noun, so we will use a lexical entry that's treated as a noun and has a somewhat different logical form, but still we can see we can still see a similarity there. And finally, for the word garden in the third phrase, we treat it as an adjective, and we pair it with a category that includes this logical form. Now, if we already look at these three lexical entries, we start to see quite a bit of similarity. For example, if we look at the first two lexical entries, we see that they include the same word, and within their categories, although the syntax is different and the logical forms look quite different, we do see some similarity, as they both use the constant house. Now, if we look at the first logical form, at the first lexical entry and the third lexical entry, we see that if we ignore the natural language, if we ignore house here and garden here, and if we ignore the actual constants being used like house and garden, we can see quite a bit of similarity between the structures of the categories. They both use similar syntax, and the structure of the logical form is extremely similar, except this single constant. So what we see is that lexical entries share a lot of information and recycle a lot of their structures. So what we are going to do to represent lexicons in a more compact way is decompose lexical entries. So we can and decompose lexical entries to the two parts that we see here. So for that purpose, we decompose lexical entries into lexims and templates. A lexical templates capture the systematic variations in word usage, and each such variation can then be applied to a compact unit of lexical meaning. So for example here, we see two templates, one for an adjective and another for a noun. And as we can see in the logical forms, we have these new constants v1. We have these new constants v1, which are placeholders for meaningful constants that can come later from the compact lexical meaning, which we'll combine with. And this lexical meaning is captured by the lexeme. And the lexemes model the meaning of words, but abstract over the compositional nature of the word and the different roles it can take as an adjective or a noun. So specifically, a lexeme includes a natural language component, which is a word or a phrase, and a set of logical constants. So given a template and a lexeme, we can combine them to recover a lexical entry. And this is a fairly straightforward process. So as we can see in this example here, the word garden replaces the constant omega, which is the placeholder for the natural language. And then we use the constants from the lexeme to instantiate each of the placeholder constants in the logical form. So specifically, garden replaces the constant v1. And at the end, from combining the lexeme and the lexical entry, we get the lexical entry for the word garden. Now, this kind of representations provide us two significant advantages. First of all, and by far the most important advantage, is that we can represent lexicon in a fairly compact way. So, for example, here in the original lexicon, we have 6 entries. However, in the factored representation that subsumes it, we have 2 lexemes and 3 lexical templates, a total of 5 entries. So already in this toy example, we can see that we get a more compact representation. More important, this compact representation also generalizes better. During testing, we can consider novel combinations of templates and lexemes to create lexical entries not seen during training. Now finally, this kind of representation also provides us another advantage as far as how we can define our model and our features. So consider that during learning, when we define our model, we can define in the original lexicon, we can define features to trigger when we use a certain lexical entry. And these features are going to be independent for each lexical entry. However, once lexical entries start to share information and they are composed from lexemes and templates, then we can define additional features. Specifically, we can define features to trigger on using lexemes, or features to trigger on using lexical templates, or features to trigger on combination of them both, which is similar to features on the lexical entry. And this allows lexical entries to share more information since they share these more atomic structures. So finally, I'll just like to give you a quick idea of what factoring a lexical entry involves. So for example, given this lexical entry for the word house, we can factor it in 3 ways. And the 3 ways differ by the number of constants that we extract from the category. So for example, here, if we extract all the constants, such as the case that we see we see at the bottom of the slide, we get a lexeme that pairs the word house with a set of 2 constants. And the logical form in the template abstracts over the 2 constants that we extracted and has 2 placeholders. However, we can also extract only this kind of factoring, where we extract all the constants, is called maximal factoring. However, we can also extract only a subset of the constants, and this is called partial factoring. And these are the 2 cases that we see here, where we get a lexeme that contains only the constant house, or a lexeme that contains only the constant of. And as we can see from the 3 cases of factorings that we have here, some factorings are better than others, and during learning we will have to learn to prefer those over the bad ones. So to summarize the first part of the tutorial, we looked at the parsing problem in semantic parsing. We started by a quick refresh of lambda calculus, and then gave you a short introduction to parsing with combinatory categorial grammars, and defined a linear model over these kind of grammars. And finally, we introduced a factored representations of CCG lexicons to allow to learn more compact and generalizable grammars. The goal of learning is to take some form of data, feed it into our learning algorithm, and output a combinatory categorial grammar. And there are two questions that we need to answer when we approach this learning problem. First of all, what kind of data and supervision we would like to assume access to, and what would we actually need to learn. So just to remind you, this is how a CCG parse tree looks like. And what we have here is a structure prediction problem. Now a CCG has two key components, the lexicon and the combinators. The combinators are a small set of operations. They are predefined, so there is no need to learn them. In contrast, the lexicon that pairs words and phrases with their CCG categories is something we need to learn. So we have a structure learning problem where we need to learn the structure of the CCG grammar. Now, additionally, with CCGs, the parsing process is often ambiguous, and we define a weighted linear model to help us choose the best parse given these ambiguities. So we need to estimate the parsing parameters. So we have these two general problems that are not CCG specific. We had to learn the structure of the grammar, so it's a structure learning problem, and we have a parameter estimation problem. And what we're going to show you is an online learning algorithm that jointly solves these two problems, learning the structure of the grammar and estimates the parsing parameters. Now, the second question that we need to ask ourselves is what kind of data we would like to learn from. And the simplest case that we can think of is go completely supervised and assume access to sentences paired with complete parse trees that include the logical form of the sentence. However, in the semantic parsing literature, what is often referred to as supervised learning actually assume access only to sentences paired with logical forms, with all these decisions here that build the parse trees being latent. So supervised learning is learning from sentences paired with logical forms, and we're going to assume access to multiple pairs of such sentences. Each pair has a sentence and a logical form representing its meaning. And building this kind of corpus requires expert annotation. It's relatively labor-intensive and includes making a lot of arbitrary decisions about representing the meaning of sentences. And an anecdote that I always like to tell when I'm looking at the supervised case is that it took my advisor, Luke, 9 months to build to annotate the 80s corpus, which is the largest supervised corpus for semantic parsing and includes around 5,000 sentences annotated with the logical forms. So alternatively, there are many forms of weak supervision where the logical form is also latent. And in general, this kind of supervision requires less data engineering. However, this comes at a cost. The supervision is weaker, and the labels don't uniquely determine the specific logical form that represents the meaning of a sentence. And in general, weaker supervision basically relies on evaluating the logical form in a system, observing the result, and comparing this result to whatever supervision that is available. So a very common form of such weak supervision is pairs of sentences paired with database query results. And during learning, we will consider many possible interpretations, execute each of them against the database, and get the result query. And then we'll compare the result against the labeled result that we have paired with the sentence, and we'll try to update our models towards parsers, towards derivations that give us the correct result, and against derivations that give us the wrong result. The equivalent supervision for instructional language is having access to instructions paired with demonstrations of people executing these instructions. And there are also some very similar examples from other domains, such as sentences paired with labeled game states and sentences paired with sets of physical objects. And the final example I'd like to show you of weak supervision is learning from failed interactions and system recovery effort. And this kind of signal is a good fit for dialogue, where it is relatively common, where the system often fails and tries to recover by asking for clarifications or asking the user to rephrase. So in this section, we'll look at the learning problem. And we'll start with a quick refresh of structured perceptron with latent variables. And then we'll show a unified learning algorithm which jointly solves the structure learning problem and the parameter estimation problem. And it's an online learning algorithm inspired by the structured perceptron. This learning algorithm will leave a few parts underspecified, and we'll give a few options for these parts, specifically for supervised data and for weakly supervised learning scenarios. We will start our overview of the structured perceptron by looking at the simple case without latent variables. The big advantage of the perceptron is that it provides us a way to do simple additive updates by only require us to do efficient decoding, meaning compute an argmax. There is close connection to max entropy models and other feature-rich models, and there are provable convergence guarantees. Given that there exists a linear separator, the perceptron is guaranteed to find it in infinite time. Of course, there is the challenge, especially relevant in our case, of how to learn with hidden variables. So this is the pseudocode for the perceptron algorithm. As we can see, it's extremely simple. We can write the entire learning algorithm in 5 lines of pseudocode. The algorithm starts, but the algorithm basically iterates over the data for t times, and then it iterates over each example, processing one example at a time, so we have an online learning procedure. For each example, we start by computing the current prediction of the model by solving this argmax problem. And then we are checking the current prediction, y star, against the provided label, y sub I. And if they're different, we do an additive update. We are updating towards the features of y sub I, the correct prediction, and against the features of the incorrect prediction, y star. Now the perceptron has this very beautiful connection to log linear models. So if we start with the log linear model here at the top, and we want to derive the perceptron update here at the bottom, the first thing we're going to do is differentiate to maximize the log likelihood. And this is going to give us this batch update where we are summing over all training samples. And for each training sample, we're getting the difference between the features of the correct example, where yi is the label provided, sorry, and the expectation of the expected features not conditioned on getting the correct label. Then we can take this batch update and switch to an online update by having stochastic gradient update. So for example, for the example I, we'll have this update I, which simply looks at the difference between the features that will get us the correct label, y sub I, and the expected features of the model not conditioned on getting the correct example. And finally, to get from this stochastic gradient update to the perceptron update, all we have to do is replace the expectations with maxes, meaning do the Viterbi approximation. So we are replacing, the positive part of the update stays the same, and the negative part, where we are updating against the current expected feature, is replaced with is approximated with this argmax, which gives us this part of the update. Okay, so now that we know how to derive the perceptron update from a log linear model, it gives us this very comfortable segue to add hidden variables to the perceptron. So, and we can start by adding, and we can do this by adding latent variables to the log linear model. So we're going to add the latent variable age, and as we can see, to get the prediction, we are marginalizing over all assignments that age can take. And the probability of y and age given x is given by this the normalized exponentiated score. So we're going to follow the same step to see what kind of a perceptron update we can derive. So first of all, we're going to differentiate the marginal to maximize data log likelihood, and we get a very similar equation. The only difference here is that we have two expectations here now. So we have the first expectation, which is conditioned on getting the y sub I, and the second expectation, which is just the current prediction of the model, only conditioned on x sub I. Then we can take this batch update and unroll it to get stochastic gradient update. Again, very similar. And just like before, we're going to replace expectations with maxes to get the Viterbi approximation. And this gives us this latent variable perceptron update. Now, as you can see, we have here two argmaxes in this case. The first part of the update, the positive part, is computed by finding the max hidden variables that give the correct label y sub I, and this is this argmax that we see down here. The negative part of the update is computed by maximizing over both y and age to get the current prediction of the model y star. So then we can take this new update rule and plug it into our pseudocode and derive the hidden variable perceptron. So just like before, the perceptron is the learner is going to iterate over the data for t times. It's going to process one example at a time. For each example, we are first going to compute this argmax, which is similar to the prediction that we had earlier. And this time, we are maximizing over both y and age. Then we are going to check if y star equals y sub I, the provided label. If it is different, we are going to do an update. To compute our update, we are first going to predict the maximum hidden variables according to the current model that will give us y sub I, the correct label. So we need to solve this second argmax here. And at the end, we are getting this final update rule here, which is very similar to the update that we see before. We have a positive part and we have a negative part, but this time both of these parts require us to compute the argmaxes. So when we are switching to latent variables, the perceptron loses all provable guarantees. There is no known convergence guarantee, and this is similar to what we see in the log linear version with latent variables, which is non-convex. However, it is still easy and relatively simple to implement, and in practice, with careful initialization, it works well. Especially for our case of semantic parsing, there are a number of modifications that are possible, including learning with lots of types of hidden information, and we can modify the update rule to add margin constraint, do a probabilistic version, use a loss function, etc. We now present a unified learning algorithm to induce semantic parsers. The algorithm handles various learning scenarios, such as supervised learning, where we assume access to pairs of sentences and logical forms, or scenarios where we have access to weaker supervision, such as, for example, question-answer pairs. The algorithm jointly estimates the parsing parameters and induces the lexicon structure. And by lexicon structure, we mean learning the lexical entries that the lexicon includes. The algorithm is related to the loss-sensitive structured perceptron that was introduced by Singh, Miller, and Collins in 2007. There are two learning choices to be made in this algorithm. The first one is to decide on the validation function. The validation function is a function that takes a parse tree and returns true or false, and it basically indicates the correctness of a parse. And we can vary the validation function to allow us to handle various forms of supervision. The second part that we need to specify is the lexical generation procedure, genlex. Genlex takes a sentence, x, a validation function v, and the current model, which includes a lexicon lambda and the parameter theta. And it overgenerates a large set of potential lexical entries for the sentence x and the validation function v. This set of lexical entries is overgenerated, it's noisy, and it's later, as we will see, it's later pruned to select the correct lexical entries to update the model. So the algorithm is online. It takes as input a training set that includes pairs of sentences x and validation function v. And there are n training examples. It processes each one training example at a time, and for each training example it processes using two steps: lexical generation and parameter update. and will now take you through the pseudocode of the algorithm and explain in detail what's going on in each step. So the algorithm starts by initializing the model. So we get an initial lexicon, lambda 0, and we use that to initialize the lexicon model, to initialize the model's lexicon, sorry. And then we initialize the weights by using the initial lexicon. It usually includes initializing all the features that are related to the entries in the initial lexicon with some positive weight. Then the algorithm starts iterating over the data. We iterate over the data for t times, and we process each example, one example at a time. For each example, we process it using the two steps, lexical generation and parameter update. In the first step, we are going to generate new lexical entries to update the model. And in high level, the way it works is we overgenerate a large set of potential lexical entries, use parsing to prune this set of lexical entries to select the best one and use them to update the model. To do this, we start by generating a set of lexical entries lambda g. And to do this, we use the function genlext that generates new lexical entries given a sentence x, and a validation function v, and its validation function vi. This gives us a large set of potential lexical entries, which we are then going to augment with the current lexicon to create a new temporary lexicon that includes many noisy entries, some of them new and some of them we'd like to add to our model. So what's going to happen next is we're going to find a way to select these entries that we would like to update our model. So as I mentioned, the two key concepts that we see already in this line is the genlex procedure that proposes new potential lexical entries for a sentence, and the validation function that giving a parse tree returns true or false and gives us an indication of the correctness of the parse. So next we are going to get the top parsers. So we're going to use the function gen. This is basically our inference procedure, and we're going to use it to get the top k parsers for the sentence xi. And next, from these top parsers, we're going to get the lexical entries that we need to update our model. For this purpose, we select the lexical entries that participate in max scoring valid parsers. And to select the max scoring valid parsers, we use this function maxvi. And it uses phi_y, which is a shorthand for our feature function. And it basically selects from the parsers in y all the valid parsers, such that all other valid parsers are scored lower than them. And this gives us the set lambda I, which is the lexical entries that we choose to update our model for this sentence. And we use lambda sub I to update the model's lexicon. Next, we continue to the second step, where we update our parameters. And again, in high level, what will happen is we will parse the sentence and we'll use the validation function to divide all parsers into two sets, the good parsers that are valid and the bad parsers. And we'll find model score violations between pairs of parsers from these two sets and use these violations to do a perceptron-style additive update to our parameters. To do this, we start by constructing the sets gi and bi. Gi includes all the max scoring valid parsers, and bi includes all the bad parsers, all invalid parsers. And to do this, again, we use the gen function and maxvi, and this is going to give us the set of good parsers. We can use gen and take only the invalid parsers, and this gives us the set of bad parsers. Then we continue with these two sets and we construct the sets of violating parsers. And for that purpose, we start by constructing and for that purpose, we define the function delta I, which basically gives us the L1 norm of the delta of the two feature functions for two parsers. And using this delta I, we can start measuring the margin between two parsers. And the margin here is flexible according to the features used in the two parsers. And what this gives us is basically that if two parsers have most of their features are similar, we will require a relatively small margin between them. But if the parsers are really different, we would like the margin to be larger. We use this margin to construct the two sets, where Ri includes all the good parsers that have a parse in Bi that is violating their score according to the margin. And Ei includes all the bad parsers that have a parse from Gi with which they create a violation according to the margin. Then we use these two sets to do an update. We update towards the positive part of the update is towards the mean of the features from the set Ri, and the negative side of the update is basically updating against the mean feature vector of Ei. And finally, once this process concludes, after t iterations and for each iteration we process every training sample, the algorithm returns a CCG grammar, which includes the parameter theta and the lexicon gamma. Now, there are a few common implementation details that we would like to highlight. For feature classes, we usually use parse features that indicate using lexical entries and different combinators. And we can also use logical form features that indicate local properties of the logical form, such as constant co-occurrence. To initialize the lexicon, we often use a list of noun phrases, and sometimes include additional domain-independent entries for function words. And finally, to initialize theta, the weights of the model, the most common approach is to provide a positive weight for the indicator feature for the initial lexical entries. So this learning algorithm leaves two parts underspecified. It's the validation function, V, and the genlex procedure that generates new lexical entries for a given sentence. And these lexical entries, as we saw, are considered and used to update our model. And the choice of V and genlex depend on the task and the level of supervision that we would like to assume access to. And in the next few videos, we'll show you two specific instances of specifying V and genlex. We'll show you how to specify V and genlex for the supervised case. So we'll specify V, and we'll show you two types of genlex procedure, one that is based on templates, and one that is based on a unification procedure. And in both of these cases, we assume access to the logical forms for the given sentences. And then we'll show you, and then we'll apply this learning to a weakly supervised scenario, and we'll introduce a new validation function that can handle that can assume access to weaker supervision. For example, a question and answer pairs rather than the logical forms. And we introduce the variation of the template-based genlex that can learn without access to the logical forms. The first learning scenario we are going to look at is supervised learning, where we have access to sentences annotated with logical forms representing their meaning. And the important thing to remember here is the parse structure is latent, so there are many latent choices to be made during learning. To apply the unified learning algorithm that we just presented, we need to specify a validation function that gives us an indication of parse correctness, and the genlex procedure, which generates new lexical entries for a sentence. These lexical entries are later considered by the learning algorithm and pruned to update the model. We will show the validation function, which is a very simple validation function in this case, and two versions of the genlex procedure. One that relies on predefined templates and allows the user to inject linguistic knowledge in this case, and another that relies on a unification process and is more language and representation independent, but doesn't allow the user to inject information in the same ease. So our validation function is extremely simple. It simply tests if the logical form at the root of the parse tree is equal to the labeled logical form. And it does that by using the function lf that takes a parse tree and takes the logical form at the root. If the logical form is correct, meaning it's equal, it returns true, otherwise it returns false. The first variant of genlex that we look at is template-based genlex. And this genlex procedure takes a sentence, x, a logical form z, and the current model, which includes the lexicon lambda and the model weight theta. And as you will notice, we are abusing the notation a bit, and instead of taking the validation function, we actually assume access to the actual logical form. And since this is the supervised case and the logical form is available, this is a relatively minor modification and allows us to present genlex in a way that is easier to understand. So genlex starts from a pair of a sentence and its annotated logical form. And in high level, what's going to happen is we first construct a set of lexemes, and then we combine them with a set of lexical templates that is predefined. And these lexemes and templates are identical to the lexemes and templates we defined earlier when we talked about factored lexicons. Now, relying on templates allows us to restrict the set of lexical entries that are available by basically providing constraints on the structure of the generated entries. And these templates can be obtained, for example, from annotating a small set of sentences with the lexical entries required to parse them, or from from a expert-driven process where an expert is using their linguistic knowledge to create these entries. And this, for example, can result in this kind of templates, where we have a template for adjective, a template for positional phrase, for a noun, for a transitive verb, and so on. Now, given these templates, what we need lexemes to create lexical entries. So we are basically recreating the process that we saw in the factored lexicon. And these lexemes is what this genlex procedure is actually going to learn. Now, if you remember, a lexeme is basically a pair of a natural language component, which is a word or a phrase, and a set of logical constants. So we will need to recover these two components to create a space of lexemes. Now, to get the natural language component, we are simply going to take all n-grams from the provided sentence. So, for example, from the sentence, I want a flight to New York, we'll get n-grams such as I want, a flight, and flight to new, and so on and on. And now to get logical constants to create the other part of the lexeme, we are simply going to take all logical constants from the annotated logical form. So, for example, here we'll get the constant flight, we'll get the constant to, and we'll get the constant NYC. And given these natural language phrases and logical constants, we can create lexemes by simply combining all of them. So each lexeme that we'll create includes a single natural language phrase, a single n-gram, and a subset of the logical constants we extracted from the logical form. Now, given these lexemes and assuming access to predefined templates, we can initialize the templates to create a large set of potential lexical entries. Now, as you can see, this set of lexical entries contains many lexical entries that are wrong. For example, they might include a natural language component that doesn't make sense, or they are paired with another language component that makes sense, but doesn't really fit the category assigned to it. And in general, this genlex procedure generates many entries, and this leads to slow parsing. As you remember, genlex returns the entries to the learner, and the learner uses parsing to prune this set of entries and select the ones to update the model. However, since we have access to the logical form, we can use some nifty techniques to do fast prunings. Basically, what we can do is use the logical form to prune the chart as we are parsing. We can prune partial logical forms that can't lead to the labeled logical forms, and we can identify those because we have access to the labeled logical form. So, for example, if we are currently looking at this pair of this sentence, I want to fly it from New York to Boston on Delta, which is annotated with this logical form. Some part of our chart might look like this. Here we are looking at the span from New York to Boston, and what you're doing right now is putting, the first step is putting lexical entries on from New York to and Boston. And next we can start combining these lexical entries. So we can see that we can use forward application here and combine to and Boston, and forward application on from New York to get this prepositional phrase here. Now, if we look at these two prepositional phrases, we see that the right one can definitely lead to the logical form. For example, this part of the logical form corresponds to what we see here. However, at no point in the logical form we see the predicate to used with the constant NYC as its second argument. So this left category can't lead to the correct logical form. This branch of the surge can't lead to the correct can't provide the correct inference. So what we do is we prune it, and we don't continue to follow this branch. And later on, as parsing continues, as the chart is being constructed, this branch is no longer explored. And as we can see, what this allowed us is to identify fairly early on that this lexical entry here is wrong, and we would like to ignore it. So let's summarize a supervised template-based genlex before we look at unification-based genlex. So in this variant of genlex, we require expert knowledge to construct the templates. In practice, this variant creates relatively compact output and clean lexicon. However, it is not language independent and it's not representation independent. Both because the templates reflect, deciding on the space of templates reflect choices that are specific to the language and the representation. However, it is relatively easy to inject linguistic knowledge and expert knowledge into the process of constructing the template, and as we will see earlier, it allows for weakly supervised learning. Before we continue and look at weakly supervised learning, let's take this opportunity to recap on what we saw so far. So we start by looking at combinatorial categorial grammars, and this is a very simple CCG parse tree, and as we can see, it starts by pairing words and phrases to categories, and this is happening in the CCG lexicon. And then these categories are combined using these operators that we see here on the side, and at the end we get a logical form that captures the meaning of the complete sentence. Now, to learn this kind of grammars, what we need to do is first we need to learn the lexicon that pairs these words and phrases to these kind of categories, and then we need to estimate the parameters that control these parsing operations. So then we continued and we showed you a unified learning algorithm to solve this problem. The learning algorithm is online, and it's jointly estimates the parsing parameters and induces the CCG lexicon. And in high level, it has two steps. In the first step, it does lexical generation. It takes for each sample, it generates new potential lexical entries to update the model's lexicon. And in the second step, it updates the parameters. and these two steps are interleaved, and each sample is processed using these two steps, one sample at a time. The unified learning algorithm left two parts to be specified. The first is this validation function, and this validation function indicates the correctness of a parse y, and it can vary according to the kind of supervision that we like to assume access to. So given a parse, it returns true or false. The second part that we need to specify is the lexical generation procedure, and this is the genlex procedure. It takes a sentence x, a validation function v, and the current model, which includes the lexicon and the parameter theta. And genlex is going to overgenerate lexical entries for a given sentence x. And during learning, we're going to prune this general set of lexical entries and pick the ones to update our model. So we applied this kind of learning to the supervised case, and showed you how we can define a validation function for the supervised case, which is rather simple. We simply compare the output logical form to the labeled logical form. And then we showed two variations of the genlex procedure, one that requires templates to generate new lexical entries, and another which is based on unification and doesn't require to predefine these templates manually. And next, we are going to apply we're going to show you how this learning algorithm applies to weakly supervised learning scenarios. So as expected, we will define a validation function that doesn't require access to a labeled logical form, and we'll show a genlex procedure, which is similar to the supervised template-based genlex procedure, in that it requires us to manually define templates, but it doesn't require access to the logical form. Okay, so what kind of supervision, of weak supervision, we can expect, what we would like to assume access to? So, for example, we can assume access to a natural language queries to a database paired with the database entries that are the response to these queries. Or alternatively, we can assume access to natural language instructions, which are paired with demonstrations of people executing these instructions. And in general, what we're going to do is we're going to execute the logical form in the system and observe the result. And this is what's going to drive the learning. It's going to be in the validation function, and it's also going to be used in the genlex procedure to generate new lexical entries. So this is exactly what the validation function does. The validation function executes the logical form and compares it to the available execution result, and this is what's going to help drive the learning process. And this execution is going to be domain specific. We still need to specify it. For example, it can be a SQL query engine that takes the logical form, executes the database, and returns the result, or it can be a robot navigating in the environment that takes the logical form and uses it to plan a path in the environment. And as we can see, this comparison here is only approximate, and this basically depends on the type of supervision available. So this allows us to assume access to a supervision that completely specifies completely the entire execution result, or a supervision that doesn't completely specify the execution result. And we'll quickly and in a second, I'll show you an example of how this looks like. Now, the nice thing about this kind of supervision is that in general, the execution function is a natural part of the complete system. So if we are building a natural language interface to a system, there is nothing that says that we specifically have to engineer the exec function. This is something that we'll have to do anyway. Okay, so let's just look at a quick example. So in the robot navigation domain, we have a robot moving in an environment, and the exec function basically basically takes the logical form, and the robot is executing and moving accordingly in the environment. So for example, for supervision, for example, we can assume access to the complete demonstrations, to the complete demonstration here. We validate all the steps, and if all the steps are correct, we consider the parse as correct. Alternatively, we can also assume access to weaker supervision, where we only have access to the final state of the demonstration and don't observe the rest of the demonstration. This is basically equivalent to pointing to the robot where it should be at the end of the execution. And if we're doing that, we're only going to validate the final state of the demonstrations, the final state of the robot execution. So this gives us a weaker form of supervision. Okay, so now that we know how the validation function looks like, we have to define the genlex procedure. And just to remind you, a genlex procedure basically takes a sentence X, a validation function V, and the current model, which includes the lexicon lambda and the model parameter theta, and it generates a large set of potential lexical entries, and this set of lexical entries is further pruned by the learning algorithm and used to update the model. So in the supervised case, if just to recap, we had access to sentences paired with logical forms representing their meaning. And we defined this process where we are extracting words and phrases from the sentence and logical constants from the logical form. We pair them to create lexemes and then use these lexemes to instantiate a predefined set of templates, and we get a set of lexical entries here at the end. Now in the weakly supervised case, we don't have access to this logical form. So this is going to break the process because we can't define this, we can't simply extract this set of constants from the logical form. So naively, we can solve this problem by using all the logical constants in the system instead. So these will be, for example, in the case of database, all the column headers and entities that can be mentioned in the database. So we're going to have this very large set of constants here. Now with this large set of constants, we can pair them with all possible, all words and phrases from the sentence. And we're going to get a large set of lexemes, which we can then use to initialize the predefined templates. And this gives us a huge number of lexical entries. So, so given this large set of lexical entries, this is not necessarily a problem because we already know that genlex can overgenerate. And the learning algorithm can supposedly handle it, prune down the set of overly general lexical entries, and pick the right ones to update the model. So let's take this large set of lexical entries and get back to our learning algorithm. So remember, in the learning algorithm, we are basically going to prune this set of the set of generated entries by parsing and taking the top correct parsers. Okay, so we have this very large set of lexical entries, and we would like to parse the sentence. Unfortunately, parsing with such a large lexicon is going to be completely intractable. So we won't be able to parse, and in practice, this is not even a matter of time. It's also a matter of the fact that the beam that we are using for parsing, is going to completely fail, since the beam will saturate very easily. Okay, so let's go back to our failure point. And remember, what we need to do is we need to find a way to get these logical constants. And we just try to take all the constants in ontology, and this process exploded and created the intractable parsing problem. So in high level, what we are going to do is we are going to adopt a coarse-to-fine semantic parsing algorithm that will allow us to gradually prune lexical entries. And the transition from coarse-grained to fine-grained parsing is going to be done using the typing system that we defined earlier on for lambda calculus. And we are going to use this typing system to define something called a coarse ontology of constants. So just to remind you, remember we have this typing system that we defined earlier on, and this typing system supports a single inheritance relation, and and this relation can be applied recursively, so we can have types inheriting one after the other. So to start building our course ontology, we will start with a set of all constants in the system. And here we are actually specifying the type of the constant, since we are going to use it. And just to give you a quick reminder, so for the constant flight, we have the type FLT, which means that it's a function from flights to truth value. And we can also have more complex types, such as the type of the constant from, which means that it's a function to functions from location to truth value. I'm sorry for the horrible handwriting. So what we're going to do is we're going to use this typing system to define define a course ontology. And to do this, we are going to first generalize these types, and we're going to do this using the typing hierarchy. We're basically going to generalize each type to its uppermost ancestor in the hierarchy. So for example, if we look at the constant flight, we will generalize it to the constant flight here that has a more general type. And to do this, we are going to take the type flight, and we're going to look at the hierarchy and generalize it to its uppermost ancestor, and this is going to map flight to entity. And if we look at T, it's already an uppermost type, so T remains T, and we get this mapping from from the constant flight to the constant flight that has a more general type. So we have this more generalized, so we have it's the same number of constants so far, but each constant has a somewhat more general type. And what we see here already is that a lot of constants that initially had different types now have identical types. For example, the constant 2, which had a binary, it's a binary function, had this type, while arrival time had this type. With the generalized types, they actually have the same type. They both take entity and returns function from entity to truth value. So next we are going to merge all these identically typed constants. And this is basically going to give us a very small set of constants. And these constants are relatively high level. They don't capture a lot of the information that we would like to, a lot of the semantic information that we would like to recover. But they do capture the typing constraints of the typing constraints of the original, some of the typing constraints of the original ontology. And we are going to use this small set of constants to solve the problem that we had earlier. Remember, we didn't know where we are going to get this set of constants from. So we're going to use this. We're going to use the very coarse-grained set of constants that we just generalized, and we're going to pair these constants with all possible substrings from the sentence, and this is going to allow us to generate lexemes, which we then pair with the predefined templates to generate lexical entries. However, these lexical entries are not really useful in their current form. They contain these coarse constants that we see here, and that means that they don't really capture the information that we would like to recover. However, what we can do with this set of coarse lexical entries, and we can further prune the space of lexical entries that we will generate later on. So we're going to prune this set of entries by parsing with the current lexicon and this set of entries. So we define a lexicon by taking this set and pairing it with the lexicon of our current model. And we parse and keep only the lexical entries that participate in complete parses, which score higher than the current best valid parse by a certain margin. And this current parse, the current best valid parse, is defined by taking the model as it is and parsing the sentence. So this is going to allow us to prune many of these lexical entries. And now that we only have this very small set of these coarse entries, we are going to go back to our fine-grained entries by simply replacing each of the coarse entries with all similarly typed constants from the ontology. And this is going to give us a set of lexical entries which is much more concise, and this is what GenLex returns. The learning algorithm then takes this lexical entry and further prunes it to select the entries to update the model. Okay, so we defined. So let's just recap what we need to use this kind of weak supervision for learning this kind of semantic parsers. So first of all, we need to know how to act in a domain given a logical form. And this is something that we naturally have to do, especially if we build a natural language interface to a system. Given that we know how to act, we can define a validation function, which will drive the learning process. And we also need to define the templates that are used in the GenLex procedure. Okay, so let me show you some results, and we look at a quick example of applying this weakly supervised learning into a specific task. So in this task, we would like to learn to interpret and execute natural language instructions, and we assume access to demonstrations of humans performing these actions. And this specific work also includes situated learning with joint inference, and I refer to the paper for the complete details. We're going to use two forms of validation. In the first one, we assume access to the complete demonstration of people executing this instruction. However, in the second, weaker form of supervision, we only assume access to the final state of the demonstration. And finally, for lexical generation, we will use a template-based GenLex like the one that we just defined. So these are just quick results from this work. And what we're measuring here is the end task accuracy of executing these instructions. Basically, we are measuring if the agent reached the desired position. And we are looking at executing single sentences and executing sequences of these sentences one after the other, a scenario that is more prone to cascading errors. So what we are comparing is the two forms of validation. So we have final state validation that only has access to the final state of the demonstration, and we have trace validation that has access to the complete demonstration. And as we can see, as expected, there is a degradation in performance between using the stronger supervision and the weaker one. We also want to see what kind of structures we recover in semantic parsing. So we took a small set of sentences from the test set and annotate them with logical forms. And what we are trying to do in this part here is match the expert annotation. And as we can see, recovering the correct logical form is significantly harder, especially when compared to executing these single sentences. And this is partly because these instructions include quite a bit of redundancy. And even if we are not able to exactly recover the logical form that captures the meaning of the sentence, we often can still execute these instructions correctly. Okay, so finally, there are a number of possible extensions to the unified learning algorithm we just showed. It can use there is work on using a loss function instead of a binary validation function, and this specifically was applied to learning from conversations. And there is also work on replacing the perceptron style updates with stochastic gradient descent, where we use approximate expectation computation that is done using the inside-outside scores of the CKY chart. Okay, so let's summarize the second part of the tutorial, where we looked at the learning problem. We start with a quick refresh of structured perceptron, and then we presented the unified learning algorithm, which is online, and it jointly induces the CCG lexicon and estimates the parsing parameters. And we applied it to two learning scenarios: supervised learning, where we showed two forms of GenLex procedure to generate lexical entries, one that uses templates, another that uses unification, and a weakly supervised learning scenario where we introduced a GenLex procedure that relies on predefined templates.